Today we will start from calculating classic golden coefficient in the case of 1 plus 1 half. This is one of the most important problems in semiconductor materials because most of the valence band or sometimes conduction band, depending on the materials, the angular momentum quantum number is 1. Then we call it P state. Either electron or hole has the spin quantum number 1 half. So here angular momentum and spin, they are coexisting. So we need to consider the coupled state. So in this case, the total angular momentum quantum number is 3 half, and then we consider the lowering the quantum number by 1, then 1 half, another lowering minus 1 half, but we don't take the negative value for total angular momentum quantum number. That's why we only have 3 half and 1 half of J. And then for 3 half, G directional angular momentum quantum number Jz is 3 half, 1 half, minus 1 half, minus 3 half. Likewise, J equal 1 half, Jz equal to 1 half and minus 1 half. When we represent their correlation between the total angular momentum quantum number and its original state without coupling, so L and Lg, S and Sg. In the case of 3 half, 3 half, so Jg is 3 half, then Lg should be 1, Sg should be 1 half. This is the only case. And then we apply the lowering operator on both sides. Here J minus we apply, here we apply L minus and S minus. Okay, and then this L minus applied only onto the first side, S minus applied only onto the second side. Then you will get this one. So this will be our homework problem. So this might be homework number 5. I guess so. It's been a while. There was no homework problem for a while. So this will be homework problem. To calculate the classic golden coefficient. Here classic golden coefficient is 1. Why is it square root to 2 over 3? Why is it square root to 1 over 3? Yeah, please calculate it yourself. And the procedure is almost the same with previous problem of 1 half plus 1 half. Okay. And this is actually a very famous problem in quantum physics if you read conventional general quantum mechanics textbook available from library, then you will see the detailed mathematical procedures. So please try yourself in the homework. So by applying lowering operator again, this quantum number 1/2 goes down by 1 to become minus 1/2. Then this one and this one also applied with the lowering operator. Again L minus plus S minus, because they are actually just the same with the J minus. So we applied again J minus. Then this G direction quantum number becomes minus 3/2. To make it minus 3/2, there's only one case here. LG should be minus 1, SG should be minus 1/2. So that's the way you can get the Clebsch-Gordon coefficient for the case of 3/2 of total angular momentum quantum number. So in the case of 1/2 with J, in this case, so JZ should be 1/2 or minus 1/2. If we consider the combination for 1/2, then LG is 0, SG is plus 1/2. When LG is 1, SG is minus 1/2. When SG is minus 1/2, it should be minus 1 plus 1/2 or 0 plus minus 1/2. And then we set the alpha, beta, alpha prime, beta prime. This is the key issue here to calculate. Alpha, beta, beta prime. To get that, you need to consider the orthogonality between this and this. Especially this 1/2 case. 1/2 case, you have it here, right? So this and this should be what? J value is different, so they are orthogonal. What does it mean? If you take the integral, so bracket representation, but actually it implies the integral. Just plus should be 0. You apply this to get alpha and beta. Likewise, there's minus 1/2 here, and you have minus 1/2 here. Then applying this and this with the orthogonality, then you will again calculate the alpha prime and beta prime. So please calculate yourself, and this will be homework number 5. Okay. The related problem is band-edge state of semiconductor in terms of this 1 plus 1/2 system. This is taken from J.H. Davis. This is a good textbook for semiconductor research. In page 381, you get those values for J-J-G combination. So especially for conventional semiconductors, the valence band has p state and hole has spin, so they are coupled. Then the J and JG combination as shown here split the energy structures into different ways. So firstly, it is heavy hole. That's the case. JG with plus minus 3 half. Plus 3 half, minus 3 half, they are different quantum state, but they share the same energy. So there is degeneracy. And this is when the LG and SG are plus 1 half, or minus 1 half. Here we are only showing LG and SG, omitting L and S because L and S are fixed. So we ignore this part for now. Okay, so make it simple. We're just following the representation of this book. Okay, this is called as heavy hole. Okay, most of the gallium arsenide materials we call it heavy hole. It is also called as A in many other semiconductors such as zinc oxide or current TMDC material. And then there is plus minus 1 half of JG, that is light hole, and then split up when J is 1 half, JG is plus minus 1 half, split up. So it is actually split up, it is separated a lot. Split up, we call it. And this energy delta is quite large, very large. It is much larger than exciton binding energy. Typically in the case of like zinc oxide related material, it is larger than like 400 million volts, so it is very large. What does it mean when this energy is very large? Hole will relax down to lower state quickly. And this energy separation between light hole and heavy hole, it is actually very small. Let's say it is delta, like on the order of 10 million volt. So this delta is often found, easily measured in semiconductors. Split off is too large, though it is very hard to measure because hole will relax down quickly or easily to the lower energy state. Anyway, this is actually just the same problem we solved in previous slide. I mean, calculating the classic Gordon coefficient. Again, you are getting the classic Gordon coefficient here. And you will see the importance again. Let me erase this for now. And this is actually a very important problem in semiconductors, and you will read the basics from J.H. Davis. Without magnetic field, we cannot distinguish different JG state here. Plus value and minus value, they have the degeneracy. Here degeneracy D is actually 2 because two different spin quantum states share the same energy. Then how about different J state? They can be split. Yeah, so they are actually split. It is called spin-orbit coupling. Okay. Please note that L is 1, L is non-zero value. When L is non-zero, there is always spin-orbit coupling. Okay, you will always see spin-orbit coupling in materials as long as L is non-zero. Not only 1 but also 2 and 3 and so on, they are all possible. Okay, then you will have spin-orbit coupling. Quite recently, TMDC material is not actually L equal 1 state. There you will see L equal 2 state, okay, in TMDC material. So things are a little bit more complicated. I'm pretty sure there will be next new quantum materials coming. So then you will see again this spin-orbit coupling in new materials, so it is important issue. Here, as I explained before, there is orbital motion of charge. It is explained here. In 3D space, electron is orbiting around the origin. Its distance is r. It generates a current. So electron is orbiting like this way, then current is generated along the opposite direction. It produces a magnetic field. So magnetic field direction is like this. Magnetic field. This magnetic field produced by the orbital motion rearrange the energy state of electrons with different J. It means actually the spin state of the electron is influenced. Okay. There is spin flipping. You will see this many times. Spin flip. Flip. It means spin quantum number is changed because of magnetic field. Yeah, this happens many cases. You will see such a phenomena in research papers. Anyway, prism electron is orbiting in a XY plane, for example. Yeah, XY plane. What does it mean? Then there is angular momentum along G direction. And there is non-zero angular momentum quantum number because it is orbiting in XY plane. That's the meaning of the angular momentum. So it is non-zero. It means LG should be plus minus 1. Plus minus means opposite orbital motion. So actually this means that LG equal to plus minus 1 means the motion in XY plane, and the orbital motion in XY plane can be represented by linear momentum representation. Here X or Y denote carrier state moving along certain axis, X or Y axis. So it is linear momentum state. This one is linear momentum state. So when it is moving along x-axis, it is large X. Moving along y-axis, it's y-axis. When it is rotating like this, it is plus. When it's rotating the other way, then it has the negative sign. Yeah, that's the representation in terms of linear momentum. It is well known, yeah, representation. You will see sometimes this one, and this is actually the same with the LG equal to plus minus 1 case. Okay. And if it is moving along g-axis like this, electron is moving along this way. Electron is not moving along xy plane, only along g-axis. What does it mean? LG is 0, right? Because angular momentum is perpendicular to the linear motion of electron, right? Because definition of angular momentum is always R cross P. So when there's a linear motion along g-axis, P is along g-axis, right? P is along g-axis. Then angular momentum should be perpendicular to that. So there is no LG component. It means LG is 0. So LG is 0, it means electron is moving along g-axis. Yeah, this is intuitively simple but important. You'll see this correlation many times in research papers. These relationships are also mathematically induced by using Clebsch-Gordon coefficient between LG and XI, but we'll skip this part because we can easily understand the intuitive picture already. To each of these can be added a spin SG. We only consider the angular momentum part, and then we add spin part, okay, additionally. And for the band edge state, this is an example of gallium nitride. Gallium nitride share the almost the same band state with zinc oxide. We call it A, B, and C state. Okay, and then the original representation of JG can be represented in terms of LG and SG, and then LG is again represented in terms of linear momentum representation here, X plus IY, which is LG is equal to 1 minus sign, yeah, minus 1. So previous representation is repeated, but we just change it into linear momentum representation here. And then this is the case when the linear polarization is along XY plane. You can excite this part. When your linear polarization is aligned along z-axis, you can excite this part. So for example, this is C-axis conventional cross axis of gallium nitride and zinc oxide. They share almost the same state. Then let's say light is instant along here. Red line is light instant direction. So it is instant like this, reflect like this. And the polarization could be chosen along here and along here. When it is parallel to c-axis, it is pi polarization. This is the convention of this series of semiconductors. And polarization is perpendicular to c-axis. It is called sigma. When you excite pi polarization, the linear momentum is only aligned along c-axis. C-axis is actually corresponding to g-axis, because this is actually symmetry axis. Symmetry axis is chosen as g-axis usually. So all of those terminologies and reasoning will be useful in your future research works. Anyway, c-axis is chosen as g-axis. So when the polarization is along pi direction, then you can excite only this part. What does it mean? A and B state are excited. The B and C state are excited by pi excitation. And here in the case of sigma, all of them, A, B, and C, are excited. Okay? So, but that is actually easily measured in experiment. So we already measure such phenomena many times in semiconductors. So for example, this is very old data I measured myself when I was a student. I just wanted to check this out. So this is reflectance, same geometry. We measure the reflectance, this one. Then for pi polarization, you have oscillation twice. sigma polarization you have oscillation 3 times. Here please note that for the reflectance, something is going up, going down, going up, going down. Then this part in the center where you have the steep change of reflectance, that's where you have resonance. Okay, that's the characteristics of any resonance peak. So you have resonance here, resonance here. Likewise, in the case of pi polarization, you have a resonance here, here, and here. That's where you have transitions. When you measure the luminescence, then you have certain luminescence peak, like here and here. It is related A and B. This state almost suppressed because it is relaxed down to the low energy state. During PL measurement, it means like there's A, B, and C. PL means photoluminescence. Photoluminescence means you excite lasers into the very high energy state. Like electron is excited here, hole is excited here, and hole will relax down, electron will relax down, and the luminescence can be observed only at the banded state after a certain delay time. So carriers are relaxed down already into the low energy state. So it's very hard to see the high energy luminescence in the case of PL measurement. So again, you will see this phenomena many times in your own measurement or in research papers. So anyway, so that's the way you can explain your reflectance. The reflectance happen in real time, there is no delay time. Once you send the light, do you think the light could be reflected directly, simultaneously, or it takes time? So the light remains here and then sometime later on it is reflected, or light is converted into electron hole pairs, and these electron hole pairs staying there at certain energy and then emit the light. No, it's not. Reflectance is almost abrupt, infinitely fast phenomena. Light is instant and directly reflected at the same time. So you don't see any relaxation here in the case of reflectance. No relaxation in the case of reflectance. In the case of PL, it takes time. Yes, there is relaxation. So their features are very different. The peaks are actually related with defect, not the band state. It is defect state. Defect states are not related with the band, right? There are lots of different kinds of defect in materials. It's very hard to explain for now. So anyway, those features you will see repeatedly in research papers. Anyway, please note that this point you have resonance, this point you have resonance, you have resonance, you have resonance here, you have resonance here. 2 resonances and 3 resonance, 1, 2, 3. So with different polarization you will see different features because of this different linear polarization. Bandage state, you can also represent those linear polarization state in terms of spherical harmonics. Let me skip this part for now. Actually, it's just the same. This is just the LG state representation. L is 1, LG is 1. L is 1, LG is minus 1. So linear representation can be also represented in terms of LG representation. Finally, we can briefly, introduce the dark and bright exciton state in TMDC. In TMDC material, if we have the one atomic thick layer like this, it is one atom thick. There's one unit cell, like the thickness of the material is just the same with lattice constant. It is even smaller than 1 nanometer. In this case, actually, for certain transition metal, the chalcogenide like WSC2, tungsten deselenide, MOSC2, molybdenum deselenide, then their lowest energy states are very different in terms of spin. Spin quantum number is -f for electron for the low state. Spin quantum number for the hole for the lowest energy state is this is -f, and this is again -f. Their difference is 0. When their difference 0, it cannot emit the light. It can emit the light only their difference is ±1. That is something called selection rule. It is called selection rule. Again, you will see this many times in research papers. Selection rule. The details are found in this paper. It's a very recent one from our group. In this case of MOSC2, electron spin is up, hole spin is down, their difference is 1. Then it can emit the light. Light emission is possible. Then we call it bright. When there's no light emission, it is dark. So WSC2 is supposed to be dark, but some people measure the light for such a long time. It's even like almost 15 years or so. People already saw the light from the dark exciton. Actually, this is the exciton state because electron and hole, they are paired. So the theoretical estimation is wrong in this case. The reason is there is various perturbation. There could be some defect. Also, there could be something called shear strain. Shear strain means the material is distorted like this way. Distorted. It acts as perturbation. When you have perturbation, the spin selection rule, this selection rule is broken. So that not only dark but also bright state are mixed. Okay, that's why this sample can emit the light. This sample can emit the light. We solved all the issues, and then we intentionally applied the shear strain by certain device structure. So we increased more and more, then this dark exciton becomes bright exciton. Then light becomes very weak, light becomes very strong. So not based on the electric field external bias, but based on the tilting of the material in 2D structures, we can make either dark or bright. So you have some sort of switching of device. And this is kind of new switching concept. Well, at least previously I was working on the thermal manipulation, and thermal manipulation is based on phonon, which is the thermal carrier, but it is extremely hard, and it is at the early stage of research. there are not so many people who is working on this area, and it is extremely hard in terms of research. We just started publishing papers only recently after struggling like 5 years or even more. But for this part of the light emission, is much easier to get published, so that's why I just, instead of the thermal properties of TMDC, we just try these optical properties, much easier to get a paper. But in the end, actually, the light and electron, it has been studied so thoroughly, extensively. So eventually you will see the heat is the last issue to solve in AI, machine learning, and the recent semiconductor structures with intense integration. You will see heat is the main issue. Then you need to study phonon again. Anyway, even though I published this paper in terms of switching of light, but still it can be possible based on some other mechanism. So doesn't matter that much. It matters, but not that great. I mean, even myself, it has been done in different ways. So in the end, I think you might be studying some research papers in terms of thermal manipulation in the future. Okay, that's it for today.